everybody hear me? Javier, you hear me?
Yes.
Okay. I appreciate the time and the opportunity in these challenging times that we're living. Is very, very difficult to maintain contact with each other. We'll have the opportunity today to discuss a topic that has been very important to me from the time I started working in Catalysis many, many years ago. And I have had the opportunity to work for both catalyst companies and oil refining companies and petrochemical companies. And the topic of how you go from discovering a material to making a commercial catalyst that will be used in a manufacturing process where the final customer is not really interested in how the catalyst was developed, but that the catalyst delivers value to their operations, and that we can have different products that we can use in our daily life. So we will go through the steps of what's the difference between catalysis and catalyst development, the difference between research and development and research and discovery. That is a very important differentiation. And at the end, we'll discuss a little bit on how and why some catalysts are shaped in the way they are. So the most important thing that we have to keep in mind is heterogeneous catalysts are found everywhere in our daily life, from the production of fertilizers, in production of transportation and heating fuels, basic chemicals in oil refineries, basic raw materials for petrochemicals, for consumer products, for everything that we use, from our clothes to our shoes to the materials we used for hygiene. Everything is related to some sort of catalytic process. In particular, the last part, the control of emissions, is extremely important. And everybody that drives a car has a catalyst cleaning the emissions of that car. There are several reports on the size of the market, and pretty much everything is around 40 billion in the US billion dollars per year, with an estimated annual growth of about 4% in the next 7 years, next 6 years now. So this is a significant economic activity, and it is interrelated to everything we consume, everything we use. And it's always in the background. Very few people really know, and even lower number understand how important heterogeneous catalysts are in our daily life. We have to keep in mind that the manufacturing catalyst is a business. And one of the issues that really impacted the way catalyst companies do business was that a global pandemic has had a strong impact on how fuels are used and the demand for transportation fuels, which went from very, very large numbers, in some cases down to negligible amounts. Entire refineries have been closed. Millions of people in the world stopped driving. So the business that came out of that was that most of the storage capacity was utilized right away, and the new business was building tanks, building a storage capacity to have fuels flowing whenever they are needed. And the other aspect is that there is a new trend, and in fact there are already plants being built to process directly from crude oil to chemicals, not crude oils to fuels, but crude oils to chemicals directly, because of the demand for plastics. This pandemic pretty much change the way we live, and we're probably never going back to how we were in the past. A lot of people are using more plastics, staying home. A lot of fuel is not being used, so it has to be transformed into petrochemicals, because that's the way we have to manage. We cannot dispose fuels or put them back in the ground. Most of what we find heterogeneous catalysts are found in oil refining and petrochemical companies. There is about 20 reaction types happening in refining, a total of about 150 catalytic processes in operation on the ground with vessels built and designed. Most of them are very, very old technologies. Hydrotreating is used for cleaning fuels, removing sulfur. Catalytic cracking is used to add value to the bottom of the barrel, getting gas oils, turning them into gasoline and chemicals. Catalytic reforming and isomerization add octane numbers to the fuel, particularly gasoline. And the last part is petrochemicals. This is what comes out of the ground when oil is drilled, is gas and liquid crude. So that is now being processed in some parts directly out of the refinery into a petrochemical site, and everything that is in natural gas, like methane and ethane, is transformed into olefins. Ammonia for fertilizers, methanols, the hydrogenation of C3, C5 paraffins to olefins as for the production of monomers for the polymers industry. And there are some smaller operations to find chemicals, like in pharmaceuticals, for example, in some cases, and edible oils hydrogenation. So to go from peanut oil to peanut butter. So there is where we can identify in this page where all these catalysts have an impact on our life, from fuels to our clothes, to our plastics, to the forks we get when we have a party and buy a bag of plastic forks. They are there. They came out of a catalytic process. Let's revise a little bit what we get here in school. Catalyst is a material that promotes a path for a reaction to happen that otherwise wouldn't. And the catalyst is unchanged, nothing happens to it. So that is the basic definition that we hear. And it is partially true, particularly because these materials are tested for a very short time. They are academic laboratories or basic research laboratories don't have much time to test for years what happens to a catalyst. It's typically the range of testing is within minutes, if at the most a few hours. They are tested for activity in a very, very small amount, because we want to test to see if the reaction happens without being masked by diffusional limitations. So we want the test to happen under kinetic conditions. And the other part is the feedstocks that are used for developing or identifying a catalyst in a laboratory. The feed is clean. There is no contaminants or poisons. So indeed, after a few minutes, the catalyst looks like new. If we characterize it before and after, it might look about the same. But that is more an artifact of the experimentation, because there is a very small time and very small budgets to basic research laboratories. So on the other hand, the commercial catalyst, a commercial catalyst is a material that has to deliver It really doesn't matter how it was designed, how it was manufactured. It has to deliver yields for the process. So it has to prove performance. It has to really maintain performance. So in order to go from a laboratory scale to an industrial scale, there are several scale-up steps that need to be followed. Typically, after a lab testing and somebody identifies a prototype and it can be made in a few kilograms, the step would go to a pilot plant or a even larger unit, a demonstration unit, to generate data that would allow us to develop a model, a predictive model, to estimate how that catalyst would perform under commercial operations. In this step, some reactions might allow to introduce the fluid dynamics in the reactor. If that's not the case, then the fluid dynamics has to be also estimated by modeling to make sure that the way the fluid flows through a catalyst bed guarantees full contact and efficient contact between reactant and catalyst. That's one part. It has to deliver. The other part is has to be able to make it. And the steps of testing performance is very, very similar. When you have a prototype, you have to be able to make it at the same quality, highly reproducible, in the kilograms or hundreds of kilograms or hundreds of tons. So you have to prove that it works, and you have to prove that you can make it and that you can deliver it to the plant. Now, the next step is you already have a material that you say it works. It's a material that you can make in the at least a few tons for commercial testing. And the first thing you're going to hear from a customer is, do you have any commercial experience? Meaning, I don't want to test it, show me data from somebody else. That is part of the negotiation that has to happen to convince a plant to give you the opportunity to test your material without affecting their daily operation. An industrial operation doesn't want change. They want to stay stable and producing and making money for the company and delivering products for a secondary market. So in that case, you have to have that. And in this specific statement covers pretty much the whole experience of developing a catalyst. You have to have data from the lab. You have to have data from a pilot plant. You have to prove that you can make it in the amounts that are needed and delivered at the time that is going to be loaded into a reactor. So that's part of having the support from different teams with different specialties to make that material available to a customer that wants to put it in a plant. The other part is you have to show that the way you design the particles, it has to match the process where it is being applied. It has to be, if it's a fixed bed, the catalyst would be different than a slurry bed reactor or a fluidized bed reactor. So the catalytic properties and the shape of the particle need to be designed to match the needs for mass transfer, for pressure drop, for heat transfer in your commercial process. The other aspect has to do with stability. No customer wants to have catalyst that dies very quickly, and sometimes it happens. It has to be very stable. It has to maintain conversion and selectivities for a long time, preferably years. And it has to be resistant to certain contaminants in order to maintain activity. Something that is very important is whenever you do a negotiation, you will have something called process guarantees. In the process guarantees, you're telling the customer your conversion is going to stay, say a number, 45% with 98% selectivity. And you are going to pay fines, or you're going to have to replace the full load of catalyst if that doesn't happen. So you also have on your end as a catalyst designer, you have to tell the customer the type of contaminants that will actually kill the catalyst. So it is very important. Those are aspects of a commercial operation. None of this was included initially in the laboratory development. So again, the most important thing is you're going to be asked, where have you tested that? You have to provide a documentation of you have a commercial plant. You have to show the quality assurance certificates of analysis that you have to provide to the customer. You have to show internally and to the customer that you have a logistics team to procure your raw materials and to deliver your final catalyst to the plant. You have to be able to convince them, and that is convincing them meaning you have to give them a good price and guarantee that your catalyst is good and that it will be there on time. Some catalytic materials may have from 3 months to 2 years lead time after the order is placed. So the coordination of your team with the customers' teams in engineering, in reaction engineering, in the logistics, permits, shipping, all that has to be included in the process of getting a material from a lab concept to an industrial catalyst. And something that is very important is every individual customer is located somewhere geographically, and those locations have different regulations. So you have to be very aware of what the local regulations are, because your material might not be welcome in that area. And you have to adjust or maybe formulate a different material that would be applied in that specific location. How do we go now from the laboratory concept? You can get designed, the active components, whether it is supporting materials, maybe mixed oxides, maybe alloys. You can use noble metals, and sometimes you have to use rare materials that are extremely expensive. You have to have a model of pricing developed internally to tell the customer, okay, I'm going to sell you the support, but the active materials, the market is very unstable, like platinum, for example, or rare earths is another case. So I'm going to have an equation that allows you to calculate the price of the catalyst by the time you buy it, because the price might change. You can, in some processes, you can use powders, which is fluidized bed or bubbling beds, or slurry reactions. Or in other cases where you have packed beds, the reaction asks for a packed bed. You can have spheres depending on one catalyst designer versus another catalyst designer. They all will tell you, okay, spheres are better for this. Others will tell you, well, not really, extrudates are better, give you less pressure drop. And some special shapes are designed, and these are particles, very small particles that are designed to minimize mass transfer limitations and increase the effectiveness of the catalyst surface. At the same time, not too complex that it will make the catalyst particle very fragile and break. either would break during shipping, during loading, or during the operation. So all that has to take place when this finally designing a industrial catalyst from a prototype from a laboratory and a pilot plant testing. So yeah, really the process determines the type of catalyst shapes that you're going to have. And what I mentioned already, catalytic cracking is a fluidized bed and train flow, so the catalyst moves from the reactor to a regeneration and then back again. So in that case, depending, there are about 4 or 5 catalyst companies in the world that are making a fluidized bed catalyst for catalytic cracking. The components are very similar and the particle configuration is also very similar. So the differentiation in some cases is these catalysts use zeolites, some they mix the zeolite and the support, or they mix the electric component in 2 different supports, or they deposit the active component. And that's part of the know-how of a specific catalyst technology. Other example is the paraffins used to produce olefins. Some vendors will have a chromium-based catalyst in a fixed bed. Other vendor for the same process have platinum-based catalyst in spheres. And in that case, the catalyst is recirculated for regeneration. So depending on the process, you might have different shapes, or even depending on the vendor and the designer of catalyst, you'll have the different process and different shapes for the same reaction. In the case of some of the environmental catalysts, for example, you can have honeycomb supporting metals, or maybe stainless steel metal sheets that are designed, both the honeycomb and the metal sheets are designed to minimize pressure drop. So in environmental catalysis. So it's really that's another aspect that has to be taking place. So if a commercial operation, a plant wants a catalyst, typically it's already arranged with a catalyst company what type of material is going to be used. We go now to one aspect that we normally have. This is a standard way of developing a catalyst, is research and development. We need to design a new catalyst. We go to the literature, and there will be hundreds of scientific papers, many technical handbooks, encyclopedias on how to design a catalyst. But most of them, if they are published, is either the know-how is already old, or it's protected by intellectual property rights. So that's an aspect that has to be taken care at the time of the research. Now, for non-innovative materials, we know now how to do it. We have identified catalytic cracking uses zeolites, hydrogenation or dehydrogenation use noble metals on alumina. Hydroprocessing catalysts will use nickel, cobalt, molybdenum. Some might use tungsten. Platinum is used for hydrocracking. Most of these supporting materials use alumina as a support. Steam reforming will use different technologies, noble metals, cheaper metals, nickel, cobalt, or magnesium aluminate, for example, has shown to be a very good catalyst for steam reforming. And emission controls is typically platinum, palladium, and rhodium. And this is an important aspect that recently, at least in the US, there has been a significant increase of criminal activity removing the honeycombs, the catalytic converter from cars, because they are trying to recover the metals. So it is very, very straightforward to do research and development for known processes, because there is a lot of information for it. The other aspect is that in order to maximize the number of prototypes and to make it faster to develop a new catalyst, particularly for innovative or new processes, is very, very time consuming and very expensive to develop a new material. So there is now the new tools is high throughput experimentation. And it's a very, very effective way of doing a lot of tests, a lot of synthesis, a large number of materials in the, sometimes in the hundreds. The challenge now is, how do I analyze that information? So the analysis of that information requires combinatorial algorithms. You need a different specialty of engineers doing that, developing mathematical models, how to process large data, databases. All that is very, very important and very, very expensive. So typically, it's a complex approach. It is very expensive to set up a lab, but it's very, very productive once you have it running to screen potential materials. Now in these times, because it is so effective, there are companies that offer those services, with the challenge that if you're working with a contractor, you really want to protect your information. So some companies are already setting up their own high throughput experimentation labs internally and generating a significant number of structures, process conditions, and the corresponding yields and conversion of these catalysts. The challenge remains still. It doesn't matter how fast you can get a prototype. Going from the lab now, in high throughput experimentation, you're talking about milligrams of catalyst being used, with milligrams of reactant being converted. So you still have to go through the standard scale-up process of going from the lab, from milligrams to a pilot plant, to maybe a demonstration plant in the middle, and then to prove to the commercial operation that you will be able to deliver and that you can guarantee a performance. Now, why do so many shapes and designs in catalyst particles? The important part in the beginning is your catalyst has to have good physical and mechanical properties for safe handling. From the time you manufacture it to put it in either super sacks or drums, the catalyst has to be robust enough to not break during shipping, during loading operations, during the actual operation, that when it contacts your reactant, it doesn't become fragile, or the particles start breaking, and then you start having issues with preferential flow, malflow distributions, because the catalyst is breaking apart during the operation. And also during unloading and disposal, the unloading process is a very challenging step, because some of these materials do break down and they cannot be removed from the reactor easily. Some of them sinter to the point that the particles attach to each other, and you will have boulders in some reactors the size of a car that has to be broken into pieces before being removed out of the reactor. All those aspects need to be taken into account when the catalyst is designed for a commercial operation. The last part is the disposal. Disposing the catalyst most of the times is a very different challenge, because now the catalyst companies might not own that material. The customer using it owns it. So the catalyst has to have the proper physical and mechanical properties to handle it, also during the operation. And the most important part is it has to be strong to deal with contaminants that typically come in an industrial stream. So if it is not, you have two options. One is you have to add, in front of your reactor, you have to add a vessel that will have a catalyst guard. The catalyst guard might be a different, maybe a cheaper catalyst that will remove the poisons from your stream before going into your reactor. That adds capital investment, because you need another vessel, or maybe 2 or 3 vessels in front, so your processing does not get interrupted. Or you can use a guard bed in front of your regular bed, and then the volume of the reactor now is smaller because you're using it to introduce a layer that will protect the catalyst. But in any case, some of these aspects can be addressed during the pilot plant range, and also during the design base. We can tell the customer that these are the limits of sulfur, these are the limits of phosphines, these are the limits of contaminants that you can see. Let me know if you see something else so I can design a better catalyst. Now, from the time you design a catalyst to the time you dispose it, as I mentioned, the demand for catalysts and new catalytic materials is increasing. There are new consumer products that are requiring better or more catalytic processes. Once the catalyst is designed, the catalyst designer or the catalyst company owns the IP formulation and also the design shape of a catalyst. And when you share it with your customer, you are going to ask for non-analysis. We don't want anybody back engineering a formulation, reverse engineering a formulation. So you want to protect that. And you put that in your terms and conditions in your contract. The other aspect is who owns the spent material. Who's going to dispose of that? Who's going to comply with the local environmental regulations? Typically, in nowadays, catalyst companies do not own the spent materials. In the past, some particularly materials that are noble metals, they used to be leased to the customer. So the catalyst company would load it and unload it, and that was it. Now it's very, very rare. What happens particularly with noble metals is that they are sent to a reclamation company that will recover that, and the customer will get some credit from the metals that are recovered. And something that is like the message for these presentations: every day, catalyst companies produce thousands of tons of the same material, sometimes in different locations, producing the same material with the same quality, with different sources of raw materials and quality of raw materials, everything within specifications in order to deliver it to a plant. So this task happens every day when industrial catalysts are made, and that's really remarkable. I mean, it is very, very satisfying to be involved in an enterprise like that, where you produce the same catalyst in Asia or in the US or Latin America or in Africa, and you deliver the same quality of product. That talks about a lot, the engineering and the discipline and the entrepreneurship that catalyst companies need to have to deliver a good quality product reliably. The frequent question that we hear is, how long does it take to get a catalyst from the lab to a commercial operation? So if it is a good prototype, meaning it shows that performance might be appealing to a customer, the business is there, meaning there is a demand for the product that the customer is making, and the catalyst will be required to deliver that demand. That is the case of propylene in particular these times. Propylene as a base for polypropylene and plastics is driving the demand for new catalysts and new formulations. So that is a very good situation for new catalysts to happen. In that case, you're talking about between 2 to 5 years to see a commercial application. If it is a completely new structure, new particles, a new industrial application, it might take 5 to 10 years before you see a catalyst in operation in a refinery or a petrochemical plant. Rive Technologies, for example, developed a new formulation of catalyst, and pretty much it took, they are already commercializing it. I'm not aware that there was already a customer using it, but it took about 10 years to get it from concept to from the lab to industrial applications. And in some other cases, I mean, because the catalyst cannot be designed properly, or the market is vanishing, or there is no market for it, some catalyst technologies are remarkably good in the lab and people fall in love with them, but that's it. There is no market for them. They are not, they cannot be made properly, and the catalyst deactivates quickly, or the particles break, or is very expensive to make. Some companies have gone into catalyst manufacturing, and after a few years, 5, 8 years, they go out of business because their formulation is too expensive. Nobody wants to pay that price. And some other materials is really companies that discover, particularly now with the high throughput experimentation, can discover new structures that might be valuable someday. And nobody knows they exist except the people that deliver them, the people that designed them, the people that tested them, the people that characterized them. And they are in reports in some files somewhere, waiting for a market or waiting for an opportunity to go from structure at a molecular level to a powder tested in a lab, to a particle shaped in a way that can be implemented efficiently in a commercial operation. And sometimes the same commercial operation after a while might go out of business because the demand for product is not there. So with that, I appreciate the time given, the opportunity to participate in this webinar, and I will address any possible questions. Thank you.
Thank you very much for the presentation, Eric. So are there any questions from the audience?
Good morning. This is Joe Marola.
Hello.
Virginia Tech. First off, Eric, I would like to thank you for a really nice talk. Many years ago, I won't even say how, I worked for Exxon Research Engineering Company. And so, you know, most of the considerations you are talking about are age old and very familiar. But the one question I have for you is the one thing you didn't talk about is that while catalyst deactivation is definitely a problem, you didn't mention regeneration, because there are a number of heterogeneous catalysts that can be regenerated in place. So what is your view on that?
Yeah, it depends on the process. There are several ranges of time in the deactivation. Catalytic cracking, for example, deactivates in milliseconds. It cooks and it dies. So it has to be regenerated right immediately. The catalyst spends about from half a second to 2 seconds in the reactor, and then it's moved to a regenerator to burn the coke. So that is the engineering of the process, addresses the deactivation and the regeneration of the catalyst. And then the catalyst goes back as regenerated material and do the process and repeat. Some other catalysts, for example, I particularly had a customer that has had a catalyst for 15 years. And that's a really bad business because they never buy anything. Because all they do is just, you sell it once and you're done. All they do is isomerization of different paraffins. depending on the market, they will make it for solvents. If it is the market changes, they make it for fuel, for octane, for the gasoline pool. That catalyst doesn't ever see any contaminants, and it will last forever. In the intermediate range, there are catalysts for some in the petrochemical plants, for example. They are deactivated by acetylene, and then you have to put a reactor that will address that before hitting your main reactor. So the catalyst will deactivate by cooking, will deactivate by poisoning, will deactivate by metal deposition, or will deactivate by the nature of the process conditions. The catalyst gets too hot, the alumina support gets sintered and loses surface area, and the reactor gets damaged. In a way, I provide technical services to refining and petrochemical plants. A case that our customer had a pressure drop issue because after 6 months, and the catalyst should have lasted 3 years. And what happened was not the catalyst, it was the insulation in the top of the reactor was a new material that they were trying, and it fell and then covered the top of the catalyst bed, and there was significant pressure drop, and they had to stop the process, remove the catalyst, redeposit a new, instead of sprayed on insulation, they had to use bricks. So everything can happen to a catalyst on the deactivation part. But some of the catalysts, for example, some of the metal catalysts will be able to be unloaded and regenerated externally. There are a few companies that will do ex situ or external regeneration, and they send it back to the customer for loading it next time or reselling it. So I appreciate, I actually know your name for some time ago. I also was in the process research labs in ExxonMobil in Baton Rouge. So it is it's something common for companies like Exxon or Chevron or BP. They have many catalytic processes in operation, and we have to deal with what happens when the catalyst is not performing. Sometimes it's poisonous, sometimes it's going bad.
Well, yeah. Well, thank you. I was actually a homogeneous person, but thank you. Take care.
Yeah. Okay. Any other quick questions?
Yes, I have one.
Okay.
In the process of developing a catalyst, how much is methodological engineering and how much is intuition?
There is no intuition. I mean, there is expertise. Sometimes we get a very highly experienced catalyst scientist that can tell you right away what catalyst to use, but he's been making mistakes for 30 years. So it's really expertise. There is very difficult. This is chemical interactions at the molecular level. Mm-hmm. That is, intuition is really perceived by some as intuition, but it's really expertise. And a lot of the work that you do, for example, working together in teams, where you can actually design a high wettability surface such that the absorption of the molecules that you want to convert mm-hmm. are not hindered by the wettability index.
Okay. Mm-hmm. We can stay in touch if you want to.
We could work on that. Yes.
Okay, and any other questions? We have 1 minute, maybe. No? Okay, I have one quick question because you mentioned as well the honeycombs and monoliths. So what are, I mean, in order to the scale up of the process for the wash coating and the monolith and structure catalyst. So what are the main challenges that you face that from going to from the lab, as you said, to scale up for that particular structure catalyst?
Yeah, the monoliths are the easiest applications that you will find, in my opinion, because you cannot scale them up.
Mm-hmm.
So whatever you do at the laboratory level with a very small monolith, most of the environmental applications, all you can do is put more monoliths. So you will have reactors that have hundreds of blocks of monolith. So every individual cell is doing the same thing. So you really don't make a formal scale up. It's just you put more of them. So every individual monolith block is a separate reactor. So what you do in the lab and what you do with one monolith, you do with 40 monoliths, you do with 50 monoliths stacked on top of each other.
Okay. Okay, it's because we have been using monoliths, and the technique they used was impregnation. Even for like a pilot plant, it was the same approach for lab and for pilot plant. I would say it would be the same for scaling up. So thank you. We can be as well in touch. So thank you very much for the presentation and the questions. So